So today I will be talking about the thermal production of dark matter with mass around eV. This talk is mainly based on the paper with this archive number. So what is dark matter? In the last century, we get to know many properties of dark matter. For instance, we know the dark matter should be very stable with a lifetime much longer than the age of the universe. We know it is very likely to be a neutral particle under the electromagnetic theory. And we also know it is cold, by which I mean that at the matter radiation equality, the velocity of the dark matter should be small enough to have a successful structure formation. And we also know the dark matter abundance or the energy density to entropy ratio, which is around the electron-volt. However, basically, we do not know the property of dark matter in the language of quantum field theory. If we write down the parameter region of generic dark matter model in the dark matter mass versus the statistic plane, we can see that the parameter region is really huge. We know somehow the lower bound. For instance, for the fermionic dark matter, we have so-called Tolomei-Gunn bound, which excludes the dark matter mass smaller than or the 100 electron volt. On the other hand, we do not know for the precise value for elementary particle dark matter at the upper mass bound. In the last century, after 1984, wind turbine became very popular. Over 10 years, it is both studied in the experimental direction and the theoretical direction. However, until now, it is not discovered. The WIMP is not discovered. So people start to consider dark matter other than WIMP. WIMP is the dark matter with mass around 100 GeV or so, and have the interaction like the weak interaction. So now people start to consider dark matter other than WIMP, meaning that we consider different kind of coupling, different kind of mass range. And in particular, I'm very interested in the light dark matter, which has a mass much smaller than the 100 GeV, the weak scale. The one motivation of the to study light dark matter is the known property, the stability. This if stability may suggest dark matter is light, because if the mass is small, usually the decay rate is suppressed. But if we consider the dark matter is light, we also need to answer some new questions compared to the WIMP case. For instance, we need to consider the why it is light, or how to produce this kind of dark matter in the early universe, and how to detect this dark matter. In particular, today I will focus on the bosonic dark matter because I will consider the E-valent dark matter. So the first question can be answered if this dark matter is composed of axion or axion-like particle or hidden photon. In this case, the small mass can be expressed from the symmetry breaking. But today, what I will be talking about does not depends what kind of particle I'm considering for the dark matter, but it apply to any of the possibilities as long as it is a bosonic particle. The reason why I'm pretty excited in discussing E-valent dark matter is because of the other two questions. Actually, there are several interesting production mechanisms of dark matter predicting the mass range around the EV range. One such possibility is Alp miracle scenario, where an axion-like particle explain not only the dark matter but also inflation. In this case, the dark matter abundance is explained as a remnant of the inflaton decay. So the reheating is incomplete. So some of inflaton remain to be the dark matter. Interestingly, in this kind of scenario, we have the around range around the EV. Therefore, we predict the EV. A similar scenario was discussed recently. It is a scenario that the axiom which explain the inflation and dark matter has the gluon coupling. If we have this action have gluon coupling, then there is QCD instanton effect contributing to the inflaton potential as well as the dark matter dynamics. So this scenario is sensitive to the strong CP phase. And we found that by requiring the successful inflation dark matter, interestingly, strong CP phase has to be smaller than 10 to minus 9. So anthropically, we may explain the smallness of strong CP phase in this scenario. And if we consider gluon coupling, then usually there are serious bound from the astrophysics or some flavor physics. But we build a model featuring GATT that the axiom can be hydrophobic and electrophobic. Again, we predict the dark matter around E billion. Today, I will discuss another kind of scenario predicting dark matter around E billion. That is the thermal production. Other than the theoretically viewpoint, experimentally, there is also some motivation to consider EV mass range of the dark matter. They are from the cosmic infrared background. It was found that the anisotropic cosmic infrared background has an excess. This kind of excess can be explained by the decay of the EV range dark matter into photons during the structure formation. Alternatively, it was found that there is an attenuation of the TV gamma ray spectrum, and this attenuation suggests an excess in isotropic cosmic infrared background. And this isotropic one can also be explained by the EV range dark matter decaying into photons. So interestingly, the two different observations suggest the similar range, mass range of the dark matter region around the EV range. Of course, there are serious uncertainty in some theoretical estimation of the dark matter distribution, and also there is some uncertainty in astrophysical observation itself. But I think the coincidence is quite interesting in different kind of observation. In the not too distant future, we can cover a large portion of the EV range dark matter decay into photons by looking at the dwarf spheroidal galaxies with infrared spectrograph installed at the Magellan Telescope or Subaru or JWST. Interestingly, only by on a 1 hours or 1 night observation, we can have very nice sensitivity. Okay, but anyway, today I will be talking about thermal production of the dark matter. And there is very famous thermal production scenario, which is called hot dark matter paralyte. The essence is quite simple. So we know that matter radiation equality happens at cosmic temperature around the electron-volt. Therefore, if the number density of dark matter is around that of the photon radiation, then immediately we find dark matter mass around electron-volt. So, namely, matter radiation equality temperature suggests the dark matter mass to be around electron-volt. And in the hot dark matter case, it is assumed that somehow the dark matter is in thermal equilibrium with the plasma in the early universe. Therefore, the dark matter naturally has this kind of relation. But as you know, the hot dark matter is already excluded because it is too hot. Thermal equilibrium predicts that the momentum of dark matter is, roughly speaking, the temperature, cosmic temperature. Therefore, the velocity of the dark matter at the matter radiation equality is around the speed of light, so it is too hot, and it is excluded. Some modification has been considered. For instance, we may consider the warm dark matter, which is the hot dark matter with some entropy dilution. With entropy dilution, we can decrease the momentum of dark matter, but at the same time, the number density of dark matter is also decreased. So to explain the abundance or to explain the correct matter radiation equality, we need to increase the mass of the dark matter. Then the Lyman alpha band or structure formation band for the dark matter turns out to be the lower bound of the mass. It is order 1 keV. So this actually is inconsistent with EV range dark matter. On the other hand, we may consider some freezing production, but it was pointed out that in the freezing case, we have dark matter lower bound even more serious than the warm dark matter case. So it seems that the thermal production of the EV range dark matter is kind of no-go. So I would like to ask whether this is true. And I will talk about that it is not true because thermal production of EV range dark matter is possible because in this case, dark matter should be bosonic one. And in this case, we have Bose-enhancement, which leads to a very non-trivial evolution of the dark matter occupation number. And therefore, I want to convince you that the EV range dark matter is still special and theoretically very motivated. The setup I will be talking about is like this. So I will consider the dark matter is produced from the two-body decay of Chi1. And Chi2 is another particle than dark matter, and phi is dark matter. I assume that this Chi1 is thermalized, so it is in thermal equilibrium, while Chi2 and phi are absent initially. The mass of Chi1 is assumed to be M1, which is much smaller than the temperature under the consideration. And Chi2 and phi are assumed to be massless. Of course, phi is dark matter, so it should have mass, but I consider this phi mass is much smaller than M1 or temperature. Therefore, I neglect the mass. In the following, what I will do is basically to solve the equations for the distribution function of Chi2 and phi. Here, Ci is the collision term. And I include the Bose enhancement and Pauli blocking effect in here. So I do not neglect it. Then what I found is that there is a burst production of dark matter thanks to the Bose enhancement effect. This burst production can be found in this figure. The horizontal axis represents the momentum of the dark matter. The vertical axis represents the number density distribution. And different contour represents the dark matter distribution at a different time. Time increase in this direction. For comparison, I also show the thermal distribution like this. We can see that the shape is very different from the thermal distribution, and the IR mode around here go beyond the thermal distribution in time. So this is the burst production. I will explain what is happening in detail in the following by separating the burst production in three stages. The first stage I call ignition. The second stage is called burst. The third stage is called saturation. The ignition stage may be easier to understand by focusing on the occupation number evolution. We can see that the IR mode around P5 burst, which is defined by the M1 square divided by T, increase until unity. And phi reach unity defines the end of the ignition stage. We can notice that the other modes than the P5 burst is not so significantly produced. In particular, for the phi IR mode is highly suppressed. I will explain what is happening by using a very simplified model for the initial stage of the thermalization. In this model, simplified model, I consider 2D space for the momentum. And I assume this Chi1 has a circular distribution. So let's consider this Chi1 decay into phi and Chi2. Let's first focus on the Chi1 with this momentum decaying into phi and Chi2. The resulting phi distribution is like this, according to some elementary calculation. So this is an elliptical distribution. Now we can consider all of the Chi1 decay, and the resulting P5 distribution is like this. We can see that the P5 is dense around this IR mode. So this mode is actually the P5 burst mode, which is M1 square divided by the typical momentum of Chi1. So the reason why this is dense is because we have circular distribution of Chi1, and they can all decay in backward. Therefore, the resulting phi from the decay in backward concentrate in a tiny phase space volume. Therefore, it looks pretty dense. This is the reason why the mode around P5 burst increased significantly compared to the other places. On the other hand, we can also see that around zero is empty. So it means that we cannot produce phi with momentum around this mode. This is, from the kinematics. Now we are ready to estimate the time scale for the end of the ignition stage. This time scale can be estimated by noting that we produce the dark matter in backwards of the Chi-1 decay, and in the small phase space volume with this P5 burst to the third. And we can see due to this small phase space volume, we have a pretty, fast time scale for this ignition stage. It is much faster than the usual thermalization scale by this factor. I remind you that the T is larger than M1, is much larger than M1 in this discussion. Therefore, this ignition happened really short period. Next, what happening is the exponential increase around P5 burst mode. This is pretty similar to the laser physics. A laser works by exciting atoms or molecules within a medium, leading to the stimulated emission of photons, which are then amplified and emitted as a coherent and monochromatic beam of light. In this case, we replace the excited mode by Chi1 and the ground state by Chi2 and the photon by the dark matter phi at the P5 burst, because P5 burst mode leads to the occupation number of unity. Then this P5 burst mode that induce the further decay of Chi1. So most of Chi1 will tends to decay into Chi2 and phi with the momentum around P5 burst. So this further increase the IR mode of phi significantly. So we get the exponential growth of the P5 burst mode in the second stage. Since the occupation number grows significantly, the phi number density also grows exponentially. We have a very fast particle production of phi at the second stage. The time scale is close to the previous stage time scale, the ignition time scale. So I will use delta T ignition to represent the time scale for this burst production. Soon, the burst production stops due to the back reaction. This is due to the inverse decay of Chi2, because we produce phi from the burst production. At the same time, we also produce Chi2 with the momentum around temperature, because most of Chi1 has the momentum around temperature, and so this temperature mode of the Chi2 also increases significantly, exponentially. When this Chi2 occupation number becomes comparable to Chi1, then we can see that the back reaction is important. So inverse decay rate becomes comparable to the burst production rate of dark matter. So further production of dark matter stops. This is pretty similar to the thermal equilibrium, but it is different. The similarity can be also found in the distribution function of Chi2 at the high momentum mode. So we can see that at Chi2 momentum around T, we have the almost the thermal distribution. It is slightly different, but yeah, it is almost similar to the usual thermal distribution around this mode. But for other mode, it does not look same. For phi number distribution, we can see it is completely different from the thermal distribution. In particular, we can see an excess in the P5 burst mode here. In fact, we can now calculate the phi number density, I mean the total number density in the saturation stage. this is that because we know the number density of chi2, we have the almost encapsulated high momentum mode. The number density of chi2 is roughly speaking t to the third. Once chi1 decay into chi2, it also decay into phi. Therefore, the number density of phi should be around that of the chi2. So we get the number density of phi to be t to the third. And this number density is dominated by the IR mode around P5 burst. So the phi produced in this way is cold. This quasi-equilibrium is kept on a very long time scale until the usual thermalization is important. But as I mentioned, this usual thermalization time scale is much faster than the ignition time scale. In expanding universe, this kind of production can also happen. This is the case when the Hubble parameter is smaller than the ignition time scale, but it is faster than the usual thermalization scale. Once this condition is satisfied at the period, then we have the burst production as discussed before. The produced dark matter momentum soon redshift. And later, we can no longer have the inverse decay of dark matter because of the kinematics. So later, this dark matter is just kept intact. Therefore, even after this period, we have the usual thermalization faster than the Hubble. It does not matter. The dark matter just kept as it is after the production. Therefore, in this kind of scenario, we can have the dark matter with number density around t to the third, but the momentum of dark matter is small. Therefore, we have the cold dark matter. The prediction is just like the hot dark matter paradigm. We have dark matter mass around the electron-volt range. A comparison of hot dark matter production and burst production can be found here by concentrating on the system of 1 to 2 process of the production. In this kind of system, we can also have the usual hot dark matter parameter region. This is the case when the thermalization rate is faster than the Hubble rate for all of the cosmic temperature under consideration. In this case, before the burst produced dark matter momentum redshift, thermalization takes place. So we get to the usual, thermal equilibrium of the dark matter, and resulting dark matter number density is the usual one. The dark matter distribution is the thermal distribution. So we get the prediction of the EB mass dark matter from the abundance, but it is too hot. On the other hand, if you consider in the burst production of dark matter, we have the relation like this at the period. And then at this period, we produce some cold dark matter. Later, it will redshift and thermalization does not affect the dark matter produced at this period. So we get the cold dark matter from the burst production. The IR mode is from a quasi-equilibrium and due to the Bose-enhancement dynamics. And this also predicts EB range mass of dark matter for the dark matter abundance. But the dominant mode is cold, and yeah, we can build such a model to have a successful for dark matter physics, including the structure formation. So this is the end of my talk. What I wanted to say is that EB range dark matter is still special and theoretically very motivated. And therefore, I think it is pretty interesting to further study this kind of EB range dark matter either theoretically or experimentally. Yeah, so far I have talked about the production of EB range dark matter. This kind of production mechanism due to the Bose-enhancement also happens in some heavy dark matter production, not just the EB range. In some freezing scenario, we need to be careful about the Bose-enhancement effect. This is the case if the chi1 decay to chi2 and phi with both chi2 and phi initially absent, and chi2 thermalization rate is much. So far, I have discussed the dark matter production around the with mass around EB. If we consider some dark matter with mass heavier than ED, this kind of burst production can happen as well. So this kind of burst production may affect some freezing dark scenarios. So thank you very much.